So now we are going to get into what organic molecules actually are and what they consist of. So we've learned a little bit about how to kind of get prepared and be able to look at these organic structures that we're going to be examining and understand what went behind actually drawing those out. And that's really important because if you don't understand, okay, the common bonding pattern for carbon is it likes to have 4 bonds and 0 lone pairs, then you won't understand if you drew a structure wrong, if you drew an isomer wrong, and so on. So that's where that background comes into play. And now we can actually get into examining these and learning about them. So the general characteristics of organic molecules, I would also say that just based off of what you will see most often is to understand that you will see carbon, hydrogen, nitrogen, oxygen. These are the most common elements you'll see. You may see sulfur every once in a while, and also maybe some of the halogens, fluorine, chlorine, but for the most part, carbon and hydrogen for sure. So carbon-hydrogen bonds are the most common. Carbon, like I just mentioned, likes to make 4 bonds and 0 lone pairs. Okay? The bonds that it forms are typically all single bonds, and the hybridization that is around these central atom carbons is sp3. So anything that forms 4 bonds around it is sp3 hybridized. The geometry, the molecular geometry that it has based off of its sp3 hybridization is tetrahedral. Carbon can also form double bonds between itself, and when you have a double bond on this carbon, you will have a trigonal planar geometry and sp2 hybridization. So this corresponds to 3 bonds around a carbon. This corresponds to 4 bonds around a carbon. And then finally, if you have carbon triple bonded to another carbon, this is a linear geometry with sp hybridization, meaning you have 2 bonds total around this carbon. Carbon forms very strong bonds between elements, and these are the ones I was mentioning. And overall, we classify carbon compounds. We have 3 main classifications, which we will talk about in just a second, but they also may have these groups, these certain groups that affect how organic molecules react, and these are called functional groups. So those are the ones we will visit in the next video. So this is a visual representation of what we were just discussing, how you can have carbon with 4 bonds, and specifically this is actually carbon bonded with hydrogen. So this would be CH4, methane. And it has 4 single bonds around it. It has sp3 hybridization, and it has a tetrahedral geometry with 109.5 bond angles around it. Here we have a carbon that is double bonded to an oxygen actually, and because of this it only has 3 total electron groups around it, right? So if you just count, keep it simple, just call them things, it has 3 things around it. So whenever you have 3 things, which more accurately is described as electron groups, this is called a trigonal planar geometry, and it has 2 single bonds, 1 double bond. Overall it has sp2 hybridization. And then finally here we have carbon bonded to another carbon here, and then it has a triple bond. I believe, if I'm not mistaken, this may be a nitrogen. So it's triple bonded to a nitrogen, and because of this it only has 2 groups around it, 2 total electron groups around it, and it has 180-degree angles, and it's sp hybridization. So these are the most common hybridizations and geometries that you will see on carbon atoms in organic molecules. As we've learned so far, we know that carbon or organic compounds, they contain carbon and hydrogen. The most prevalent, so the bonds that come up most often, and you will see most often in organic molecules, are carbon to carbon single bonds and carbon to hydrogen single bonds. These bonds are nonpolar, and what this means is that they don't have a huge difference in polarity, which makes them a more equal sharing of electrons between this bond. So what this means in terms of solubility, so whether it dissolves in water, for example, water is very polar. So that's something to note, is that water is very extremely polar. So this solubility, this concept of solubility plays on the fact that like dissolves like. So polar molecules like to be dissolved in polar solvents, and nonpolar molecules like to be dissolved in nonpolar solvents, or whatever it is that you're mixing, they like to be similar to each other. So just think about how your friends, usually the friends that you make organically, no pun intended, are those that like have similar backgrounds to you, right? Or it's the easiest, right? At least like for me in college, I became really good friends with people who had similar backgrounds as me, and we all lived in Houston. We all had just things in common, right? Or you end up having things in common. Like by the end of college, having gone through that experience together, you have so much in common. Having gone through so many classes together, you end up having a lot in common, so you stay friends for the rest of your life. But anyway, molecules are kind of similar, where they like to be with similar, quote unquote people, right? Molecules as themselves. So solubility in water is very low for many organic compounds. Organic molecules like glucose, which contains carbon, any of these black circles in these space-filling models are carbons. They contain hydrogens as well. Any of these white circles are hydrogens, and the red are oxygens. So you can see that it contains nothing but carbon, hydrogen, and oxygen. These, although it is an organic molecule containing, single CH and CC bonds all throughout, it has groups within it. And these groups, and let me erase so I can kind of point out in a different color because it's hard to see. These groups are actually OH groups, and we will talk about those in the functional groups video. But these groups allow for similar interactions to be occurring between this and water, which is superpolar. So having those polar groups make the overall molecule soluble in polar solvents. And then finally we have, as an example to illustrate this solubility example, molecules with long nonpolar regions and polar regions act as surfactants. So if you remember from the solutions and colloids module chapter, we learned about how soaps, so how detergents and surfactants work. And that is that they dissolve any grease or oil with their nonpolar tail, and then the polar head is able to dissolve really well with water. So in this way, it forms a micelle around any grease or dirt, and it washes away in the water with the polar heads on the outside being able to be miscible with water. So there are 4 types of hydrocarbons. Hydrocarbons, as the name states, or as you can kind of guess from the name, consists of only carbon and hydrogen. They are grouped based on the number of bonds between carbon atoms. So these types, it's grouped based off of the types of bonds. So alkanes. This means that you have nothing but single bonds. Alkynes, you will have a double bond somewhere within that molecule. An alkyne is whenever you have a triple bond within that molecule somewhere. And then finally, aromatic. This is whenever you have a ring, and this ring, and I'm doing a horrible job. I have been out of commission with organic molecules for a very long time. I'm doing, yeah, so I drew an aromatic, this molecule specifically, benzene. So I drew the line structure, which we will discuss in just a few slides, but this molecule has kind of what I like to, kind of visually see just as a pattern. It has double bonds and then single bonds, double bonds and then single bonds, and it's a ring usually. So this is what aromatic compounds typically look like. Aromatic, defining compounds as aromatic, it goes a little bit further than that, which if you take organic you will learn, but like it's actually really specific to describe certain compounds as aromatic or not. But these are the 4 types, so you will see either all single bonds, not all double bonds, but I mean you will have a double bond somewhere within that compound, and it can be classified as an alkene. So I just realized this has a huge typo. This should be alkene, and then this one's alkyne, and then aromatic. So some properties common to hydrocarbons is the overall increase in boiling point based off of the size. So we learned about this way back when in chapter 1 about intermolecular forces. So we learned that the bigger something, by something I mean a molecule or structure, the bigger a molecule is, then the more chances for dispersion forces, which means you have more IMFs overall, which leads to having a higher boiling and melting point. And you can see this displayed here, where we start off with a really small structure. So its boiling point is super low, and it's so low to the fact that it ends up being a gas. Like for us, for example, room temp, usually the, environment is above this type of temperature, right? So what you'll see is that because of that, it's boiled away already. Like the temperature causes it to already be in gaseous form. And then as you get bigger with these molecules, or as these molecules get bigger, the boiling point starts increasing, so you actually end up having liquids. If we were to actually see the states of these different molecules. So some common uses, and this also goes back to the state of these. So methane, propane, and butane, these are all very small hydrocarbons in comparison with bigger hydrocarbons. So methane in natural gas, propane in bottled gas, butane in disposable lighters. So butane, I think for sure it's a liquid, but these two are gases versus this is a liquid. And then we know that all of these bigger hydrocarbons, for example, octane, is in gasoline. So these are some common uses of these alkanes. Notice that it is mostly all for burning or for generating some sort of heat to either cook or drive and be the energy source for some sort of engine. So it's because hydrocarbons have a very exothermic, they are very exothermic whenever they are combusted. So now let's look at how we actually write out these formulas. So we've looked at some carbon compounds, some hydrocarbons, but they may have been confusing because, besides the Lewis structures that we learned about, we haven't really discussed more types of formulas. So there are a few common methods for writing structures in organic. The structure formulas show how the atoms are bonded to each other, and this is most likely what you will see. There are condensed structure formulas, which condense the groups together to little groupings, like this one, or like this one, in comparison to the regular structural formula, which shows every single bond between every single atom. So this right here is just a regular structural, and then this one is a condensed. So you can see how, for example, this group right here, CH3, this is referring to this right here. And then we have CH2. This is referring to this group right here. And then basically what splits them up is the bonds between the carbons right here. Right? That's what's splitting each one up. So these two molecules, and I made this meme, by the way, so proud of myself, but they're actually the same exact thing. So, you know, if somebody asked me, I would tell you these are the exact same thing. How do I know these are the exact same thing? They look a lot different, right? This one is showing the bonds, the lone pairs, every single atom, and this is like just some lines. What is that? So we're about to learn what these are. And these are the bond line, aka zigzag formulas. So you can call them zigzag, I don't mind, or just bond line formulas. So this type of formula has nothing but lines, and what it ends up showing is the bonds between carbon atoms. So carbons are actually no longer drawn, and instead they're replaced by the ends and bends of a line. So for example, this is the end of this, so hold on, let me show you a pointer. Okay, so this right here is the end of the line, right? This is a bend. Those two, I know they're different, like they're like, this is an end versus a bend. I know they're different, but they both show a carbon. So I'm going to draw it in, carbon and a carbon. H's have been omitted. So it's not just, oh, carbon bonded to an OH. No, that's not what is going on here. They've been omitted, but they actually are there. And over here we have a carbon bonded to an O. Now here is a little note that I think is super important, so make an asterisk. Notice how OH is drawn with the bond to the second carbon, but it does not mean that there is a third carbon right there at that end of that bond line. It just means that carbon is directly bonded to oxygen as shown on this structural version of this same molecule. So these molecules, if you look at them, they are actually exactly the same. I'm just making this a little bit cleaner. So we have a carbon, a CH3 bond, a CH3 group, sorry, right there. And then we have a CH2, that's there right there. And then we have an OH. We have an OH. So you can see that we have the exact same molecule. Now, how did I know how many hydrogens to draw in? I knew that because I know these are normal carbons and they are happy carbons that have 4 bonds around them. So I saw that this carbon, for example, had 1 bond going that way, 1 bond going that way. That's 2 bonds. So all that was left was 2 hydrogens to draw in. So that's how I knew how many hydrogens to draw in. You go based off of what's already there. Here are some more examples. So again, we're going to draw in a carbon at every single bend and end. So we have a bend here, that's a carbon. We have a bend here, that's a carbon. We have a bend here, that's a carbon. We have an end here, that's a carbon. We have an end here, that's a carbon. Remember, carbon wants 4 bonds, that's the magic number. So however many hydrogens are missing, or however many bonds are missing total, then that's how many hydrogens you're going to draw in. So for example, and I'm going to show the laser pointer. For example, here, this carbon has 1 bond to this oxygen. How many bonds is it missing? It's missing 3. So we are going to draw in 3 hydrogens. And this is assuming that you don't have any, like here we have this is, oh, so sorry, I forgot to mention this. These are the exact same, these two. That one and that one. This one and this one are also the exact same. Okay, so you can go ahead and do the same thing for this one on your own. But what I'm going to do is draw in all the carbons and hydrogens missing on this top right hand molecule. So far I drew in those 3 hydrogens. Another thing you can draw in is lone pairs, just because you know the bonding patterns now of each type of atom. So we know that oxygen likes to have 2, it's not letting me draw these lone pairs on. Okay, there. Oxygen likes to have 2 bonds, so that bond, and 2 lone pairs. So that's why I'm drawing those in. And now I'm going to draw in every atom missing on this structure. All the hydrogen, sorry. So this carbon on this end has 1 bond. So I'm going to draw in 3 hydrogens. So what I'm doing, the reason I'm drawing in, not because it's necessary, the structure is already like complete. Like this one is already complete. I'm drawing it in so you can see what is being omitted, so you can, like the other way around, once you get to organic chemistry, you can actually draw the line structures and understand what's going on behind them. Okay, and then we have this carbon here. It's missing 1, so it needs 1 more hydrogen. This carbon has 2 bonds already, so I'm going to draw in 2 hydrogens, and then I erased this carbon, but it's missing 2, so 2 hydrogens. And then this chlorine, it has 3 lone pairs, and I know it's actually omitted. What a bad textbook drawing, like example that they gave me. Anyway, it also has 3 lone pairs. Halogens like to have 1 bond, and they're 3 lone pairs. So behind all of that, just behind those lines, what actually was omitted was all of this. So it's a lot of information that's omitted from these bond line structures. So I'm going to erase it so you can see the difference. Like all of that information within just this little, these few little bends and lines. So there is a lot to these structures, but the whole reason and the purpose for them is that they save a lot of time. So you see how having to draw in all those hydrogens took more time in comparison to just drawing in this type of structure.